When you send an Axios HTTP request, depending on the HTTP protocol, that request will get into either a TCP segment or a quick segment if you're using HTTP3. But eventually that segment will end up into an IP packet. The destination IP address will be placed in the packet, and the source IP address, which is your machine's IP address, or your routers if you're behind NAT, will be placed on that packet. When you send a SQL query to a Postgres server, that SQL query string will be placed into one or more segments because it could be large and it might exceed the maximum segment size. And those segments will be placed into an IP packet. The destination IP address will be the Postgres server. The source IP address will be yours. Same thing when you do a query to get a key from a Redis server. When you're watching this video or listening on the podcast, YouTube or Anchor in my case will package the data into TCP segments. And these segments, if you're using TCP or UDP in certain streaming protocols, those datagrams or segments will be placed into an IP packet. The destination will be your machine or your router. And those will be, and the source will be, in this case, YouTube's or Anchor's. So everything end up as an IP packet, and all the routers that are in the middle only sees that. Most routers don't even care about what is inside the content. Could be a database query, could be an HTTP request, could be an encrypted HTTP request. Most of them are, but we don't care. And that's the beauty of the internet protocol. It is completely agnostic of what's up what is the upper protocol is. That is not a completely entirely true statement, because there is a bit in the IP header that tells the router what is the protocol that is inside the content. If I'm not mistaken, this bit was added for performance user. We do this all the time with metadata in backend engineering and the front-end engineering. We add metadata to avoid cracking up data or parse things, right? To find out what it is, we add hints about what this thing is so that we can only read the headers and find out quickly whether I want to block UDP, for example. I can immediately know this IP packet is a UDP, or it's this or this, right? Or the other. So the idea is everything end up as an IP packet, and everything is in the internet is IP, and that's the name Internet Protocol, and that's the title of today's podcast in the Backend Engineering Show. How about we just started? Welcome to the Backend Engineering Show with your host Hussein Nasser, and today's title is IP, Internet Protocol, a wonderful, simple, elegant, agnostic protocol that was built and made a scale to the whole wild web. Wild web. World Wide Web. It is a wild web if you think about it, with all the danger and the excitement out there. But the IP protocol, before it was designed, we had the idea of peer-to-peer communication to send data from one machine to another machine through the concept of networking. And to send packet from one machine to another machine, send data, we use a unique identifier. We used to use a unique identifier called the MAC address, which is the Network Card Media Access Control ID, effectively. And that is global. That ID is global, and it's available in every machine, and no two machines theoretically can have the same MAC address. So why don't we use that? The problem with the MAC address is non-uniform. It's random, almost. There are some, some bits describe the manufacturer, the type of the machine or whatever, but it's still there is no uniformity when it comes to MAC address. If I give you a MAC address and I give you a bunch of machines, just like databases, when it comes to full table scan, you got to scan all the machines to find what this MAC address actually live in, which machine does it live in, right? Because got to scan them one by one. You can create clever indexes, but those indexes have to be stored somewhere and have to be updated all the time. Still, it is very problematic to scan everything. So imagine scaling to the whole worldwide internet. You can't. There are billions and billions of machines. How do you scan all of them to find, oh, here's a MAC address, go send it to there? It's like, how would I know? You can build all sort of clever things with stateful protocols to say that the routers will have nodes that, oh, this MAC address was on this port, right? Just like bridges and switches work today, but at the global scale. But those tables will be so large, right? And it won't scale because we're addressing individual hosts. So that idea was dropped. It's like, hey, we won't scale. Yeah, MAC addresses are beautiful for a small network. And let's scan the entire thing and let's eliminate it by using switches. And switches can have like a sort of table. And yeah, we're going to work with 100, 300, 400, 500 machines locally, sure. But in the billions and the millions, no way. So we need a new protocol. And we need a new addressing system. And we needed two parts. The first part is to identify the network. And once we identify the network, we isolate the number of hosts in that network. And this way we can slash the number of searching space. If you study graph theory, you might know this, right? The idea is here is just like databases. We want to eliminate the search space. I always say this in my database course. The best way to work with a billion row table is to avoid working with billion rows. That's the best way. There isn't any other way. You never work with billion rows. Yeah, big data tries to do that, right? Because there are sometimes you cannot avoid it. You have to scan the whole thing to calculate aggregates or maximum count or averages. But most of the time, the best way is to eliminate working with this. And to eliminate, you use indexes. And IP is kind of an index in a way. The idea of having two portions in the IP concept, the internet protocol, have a network and then have a host. By doing that, every router will look, oh, which network is this? I don't care about the host. Just let me know. Is this thing in my network? And if it's not, let's forward it to a router that knows the network. This cycle keeps happening until we reach a router that it is in its network. And once we find that, now we have a limited sets of hosts to 55,000, maybe 500. But that's pretty much it. Let's search. And now we can send that. And now we can safely use the MAC addresses at a lower scale. Right? So that's the idea. So every IP address has two portions, the network address, right? And the network portion and the host portion. And it's identified by this classless, /24/16/30/31. That's a very small host, but that's the idea. That's the beauty of this. And at the end of the day, this is what scales the internet. The concept of an IP address, right? And now, while this causes another problem now, because now the computer technically have now two addresses, right? This IP address and this thing that's called MAC. We still need the MAC address because I'm going to use that to address thing locally. Because imagine, when I send data from one machine to a machine, we still use the MAC address, right? But now, most of the things out there only know of the IP address. We almost never memorize the MAC address. Well, think about it. We never always memorize the IP address. Why? Because we have DNS. But the DNS maps to an IP address, right? So we memorize the name of the host. and the host is resolved to an IP address, and the IP address, at the end of the day, when you reach the network that is actually yours, you need to convert the IP address to a MAC address. And that's another protocol that's called ARP. Probably another topic. Address Resolution Protocol. So we talked about the IP. Why do we need the IP? We were talking about the concept of IP address with these two segments, network and host. And now routing through the internet happens because we identify the network portion and the host portion. And this allows us to build the routing tables. We still need tables, right? So, okay. So let's say I want to get to this IP address. Okay, what's your network? This is my network. Well, so the last time I checked, this kind of port, if I send the IP packet through this port to that router, it will get you through this much hops. It will give you the network. And you can also get through this router, through this port. So there are multiple paths. That's beautiful and also dangerous, right? Because of this different path in the IP, one packet might go to a certain route. The second packet, which while going to the same destination, might take a different route based on the congestion, based on the shortest path algorithm at that state. Because this routing table keeps growing and growing and growing, and it will change all the time. Routers get shut down for maintenance, so they will disable them. So the IP packets need to take a different route. So this means IP packets will arrive at the destination most probably out of order. That's why we need a higher level protocol to order these packets, check for integrity, right? IP packets might get lost. The IP protocol has no business of ordering. The IP protocol has no business of free transmission or doing any of that. It's a simple protocol that is allow you to do this route, and that's it. Once you reach the packet reaches the destination, its job is done. Even if it doesn't reach, it's not its job. It's like, hey, I tried. Hey, packet got dropped. What do you want me to do? So imagine the routers, poor router here. The routers get flood of IP packets. They don't care, as we said. It's like, what is inside this packet? They might have priority set, but packets are packets, IP packets. Each packet will have a destination IP address and a source IP address and a bunch of headers. So to route is to read the headers and parse the network portion and then figure out, look up the routing table, and then forward based on this algorithm. That takes time. So each packet will take few hundred nanoseconds, maybe a few microseconds, maybe up to a millisecond or two. That's harsh, but it will take finite amount of time to be processed. What does that mean? That means I have a bunch of packets. So if each one took time, that means packets have to wait, which means I have to have a place for them to wait. But what if this place gets filled up? My buffer get filled up as a router, right? That means I have to drop packets. And when packets are dropped, it's not responsibility of the router to tell you that. You as a sender or receiver in this case need to understand that something got dropped, have a timeout, and all of this is built on higher level. So it is built on the TCP protocol, right? And it was rebuilt, if you will, on top of Quick, which sits on UDP. UDP doesn't have that. It's also as simple as IP. But Quick rebuilt that in a smarter way to have context of streams, but is also built the idea of knowledge of retransmission, retries, all that stuff. But here's something I wanted to do. Smart routers these days, before they drop the packet, because of this idea of congestion, right? Some smart routers will send something called the notification, which says, hey, I'm going to give you a grace period. I'm starting to feel a little bit of a congestion in my network, and I'm gonna tell the receiver, because it takes the IP packet and try to send it to the receiver, right? I'm gonna tell somehow the receiver that I'm about to experience congestion. So I want you to slow down sending those packets, because you guys are, in Arabic we say مسختونها, which means you're trying to exaggerate a little bit. So now slow down. So how this is done through a special header in the IP protocol called ECN, explicit congestion notification. So it will set that bit, the router will set that bit, says, okay, true, hey. So we're setting it at the layer 3 here. We didn't mention that IP is layer 3, right? And the packet will go its merry way and will reach the receiver. The receiver will read the IP packet and will read that bit. So, we're experiencing congestion. So it will tell the higher levels like TCP that, hey, we just experienced congestion. Let's reduce our congestion window. And I talk about this in details in my networking course. Check it out. Go to network.husseinnasser.com for a coupon. So now the higher level will start reducing the window, so the IP packet volume will slow down. But this protocol, right, the explicit congestion notification is so brilliant. So this is a way to message lower level to a higher level while remain stateless in a manner, if you think about it, at that layer, because we're sending all the data we need through the IP protocol. Without the ECN, we will have to go the hard way of dropping packets and hitting timeouts to reduce the congestion. With the ECN concept, what will happen here is the sender and the receiver and the router will start to communicate to slow things down before packets are dropped. Brilliant. Absolutely brilliant design. So I absolutely love it. So finally, because of this elegance, having the IP packet carries data, at the end of the day, anything on top of the IP is just data. So no matter what protocol you use, if you're browsing the web, if you're watching a YouTube video, if you're connecting to your databases, if you're on Teams, Microsoft Teams, if you're chatting, if you're coding, if you're doing anything that has to do sending any data, you're going to either use UDP or you're going to use TCP, right? These are the only protocol available at layer 4. You might directly build your own protocol on top of IP. That's rare. Some protocols like ICMP is directly built on top of IP. It's a layer 3 protocol. But eventually, everything is IP to be routed on the internet. And just that idea gave birth to the concept of VPNs, right? It's like, before we talk about the VPN, because now everything becomes an IP packet, where is the first hop that your packets go to after your router, that is? Your ISP, right? Because your ISP is your gateway to the internet. It will take your packet and will see if you have a connection, if you have a bandwidth, if you paid your bills, and it will forward based on that to the wide internet. So your ISP clearly sees the IP destination that you sent it. It knows any site you access. It doesn't necessarily know the content of the data because most everything is encrypted these days. So ISPs don't see the content, but they know. They know the port. Port is layer 4, but they know that. And they know the IP address. So ISPs know every site you visit. If they reverse engineer, obviously, the IP to a host, right? And if you are obviously using their DNS, right, then the DNS request itself is a UDP packet diagram that fits into a UDP packet, right? That fits into an IP packet that gets sent. So the destination and the UDP is unencrypted unless you're using DOH or DOT, but it's unencrypted. So they still can read your DNS request because they are just IP packets at the end of the day. So everything passes by your ISP, right? So VPN thought, okay, since in the client side, everything is sent eventually as an IP packet, what if we took that IP packet with the destination IP address, with the source IP address, and shoved that content with everything, the destination, the source, and the data, into a brand new IP packet as data. So the new IP packet, because the data of the new IP packet is the old IP packet that you want to send. And now the new IP packet destination becomes the VPN IP address. And the source, still, it's your IP address. So now we masked what IP address, and we're going to encrypt that inner IP address content. So now if we send this content, all the ISP sees is a bunch of IP packets going to one IP address, which is the VPN IP address. It's just seeing a fleet of IP packets going to that VPN address. The VPN then cracks open that IP address packet, the IP packet, and then decrypt that, assuming there was a handshake to establish the symmetric keys, and then decrypt that. And now it knows, oh, you want to go to this destination. So it will basically reroute. The VPN will send the IP packet. So the VPN's ISP know where it's going, but its source IP now it becomes the VPN. You are never revealed at the end of the day. The VPN knows who you are, obviously, because you sent it the IP address, right? So you send it the packet, so it knows the source IP. But nobody else knows. The ISP sees that you're always going to this VPN, this IP address. The VPN knows that you're coming from it, right? But the VPN will hide your source IP address and uses its IP address effectively. So that's one way to do it. This is called IP in IP. That's one protocol. Another protocol, OpenVPN, uses UDP. So what VPN will do is we'll use the same concept. Let's do the IP and put that IP packet in an UDP diagram, and then put a destination port, destination IP address. Now we have a port. In the previous one, we didn't even have a port. Okay? Now we have a port because it's layer 4, right? Layer 4 is what exposes the ports. And now we add that destination IP address, destination port, and send all the content to this port. That UDP diagram becomes another IP packet that will send to the destination OpenVPN server. So the way we built the internet is just so fascinating, with the way everything is isolated. Looking at the layer 3 as just layer 3, you can build all this innovation with the concept of VPN and all of that. But this video is not about VPN necessarily, whether it's good or bad for you. It's just what it is, right? Take it or leave it. Now, with this understanding, you might be able to answer all the questions that you have about VPNs, really, because now you understand how it works. It just doesn't really give you any more than that. Thus, I thought I would talk about the IP protocol. It's so elegant and beautiful, so simple if you think about it this way. And I always wonder if we can build our own protocol on top of IP directly. But then, especially because you don't really need you building a protocol that doesn't really need the concept of ports or processes. It's just your whole host is just one thing, right? You're just addressing that host directly. I don't care about ports, right? So you can eliminate the concept of the 8 bytes that you add for UDP and the 20 bytes header that you add for TCP, and stuck just with the 20 bytes IP header effectively, just saving a little bit of extra bandwidth, saving a little bit more, and I wonder how much we can be more efficient, saving 8 bytes, right, and building things on top of IP directly, if the use case decided to, can be really beneficial. So that was something I think about. Like, while UDP and TCP are beautiful protocols, you know, they are general purpose, right? There is special use cases where, for those advanced engineers who don't want all these bells and whistles. They want, just give me a way to write my content as an IP packet and let me send it. The problem is, what I don't know is, there is a bit that's called the protocol in the IP header, and I don't know if the packet will be rejected if you built your own custom protocol. Right? It gets really interesting, and these are questions that I don't have answers for, but this is what I want to talk about. Hope you enjoyed this episode. Gonna see you in the next one. You guys stay awesome. Goodbye.